We all experience gravity. It's an invisible force that pulls us towards the Earth, keeping us grounded. Whether we're walking on a busy city street or jumping on a trampoline, gravity is always at work. It keeps our feet on the ground, ensuring we don't float away into the sky. This force is so fundamental to our daily lives that we often take it for granted. But gravity does more than just keep us grounded. It keeps Earth orbiting the sun, maintaining the delicate balance that allows life to thrive on our planet. It's a fundamental force in the universe, governing the motion of stars, planets, and galaxies. Without gravity, the cosmos as we know it would not exist. But here's the thing, we don't fully understand it. Despite its omnipresence, gravity remains one of the most mysterious forces in nature. Sure, we have Einstein's theory of general relativity. This groundbreaking theory revolutionized our understanding of gravity, describing it as the curvature of space-time caused by mass. It describes gravity beautifully on large scales like planets and galaxies. Thanks to Einstein, we can predict the motion of celestial bodies with incredible accuracy. But when we dive into the microscopic world of atoms and particles, general relativity doesn't quite fit. The rules that govern the very small are different. The problem is that the other forces of nature, like electromagnetism, are described by quantum mechanics. This theory explains the behavior of particles at the smallest scales. Quantum mechanics governs the interactions of tiny particles, providing a framework for understanding the fundamental building blocks of the universe. Gravity, however, remains stubbornly resistant to being quantized. This means we can't yet describe it using the same principles that apply to other forces. This mystery of gravity has puzzled physicists for decades. The quest to unify gravity with quantum mechanics is one of the biggest challenges in modern physics. Can we bring gravity into the quantum fold? Scientists are exploring various theories and conducting experiments to find an answer. The answer might lie in the hunt for a hypothetical particle called the graviton. If discovered, it could bridge the gap between general relativity and quantum mechanics, unlocking new understanding of the universe. To appreciate why gravity is so enigmatic, let's look at the other fundamental forces. We have the electromagnetic force, responsible for electricity, magnetism, and light. This force is carried by particles called photons. Then there's the strong force, which binds atomic nuclei together. Gluons are the particles mediating this force. Finally, we have the weak force, responsible for radioactive decay. This force is carried by W and Z bosons. These three forces are all explained within the framework of the Standard Model of particle physics. This model is incredibly successful in explaining how particles interact at the quantum level. However, gravity is conspicuously absent from this picture. Quantum mechanics revolutionized physics in the early 20th century. It introduced strange new concepts. Particles can also be waves. Uncertainty is inherent in nature. The act of observation can affect the observed system. These ideas were radical departures from classical physics. But they were essential to explain phenomena like the behavior of atoms and the interaction of light with matter. Quantum mechanics has led to groundbreaking technologies like lasers and transistors. But gravity, stubbornly, refused to be quantized. General relativity, Einstein's masterpiece, treated gravity not as a force but as the curvature of space-time caused by mass and energy. The problem is that when we try to combine general relativity with quantum mechanics, we run into trouble. The equations break down. We get nonsensical answers like infinities. This suggests a fundamental incompatibility between these two pillars of modern physics. This incompatibility is most evident in extreme environments like black holes or the very early universe. These are realms of immense gravity and tiny scales where both quantum mechanics and general relativity are crucial to understanding what's going on. This is where the need for a quantum theory of gravity becomes most apparent. We need a theory that can reconcile the macroscopic world of gravity with the microscopic world of quantum mechanics. Section 5. Enter the graviton. This is where the graviton comes in. Just like the other forces are mediated by particles, physicists theorize that gravity is also carried by a particle, the graviton. This hypothetical particle would be the quantum messenger of gravity. The graviton is thought to be massless, like the photon. This is consistent with the fact that gravity's reach is infinite. Additionally, the graviton should travel at the speed of light, explaining the instantaneous nature of gravitational interactions. Finding the graviton would be a major breakthrough. It would confirm that gravity, like the other forces, can be described within the quantum framework. Section 6. The elusive graviton. Why finding it is so hard. However, detecting a graviton is a task of unimaginable difficulty. The graviton, a hypothetical elementary particle that mediates the force of gravity, remains one of the most elusive targets in modern physics. The main reason is that gravity is incredibly weak compared to the other forces. While we can easily observe the effects of gravity on a macroscopic scale, such as planets orbiting stars, its influence at the quantum level is minuscule. The electromagnetic force between two electrons is billions upon billions of times stronger than their gravitational attraction. This stark difference in strength makes it extremely challenging to isolate and detect the graviton. This weakness translates to an incredibly small probability of a graviton interacting with a detector. Even the most sensitive instruments we have today are not capable of picking up such faint signals. To have any hope of detecting a graviton, we would need detectors of astronomical size and sensitivity, far beyond anything we can currently build. The scale of such an endeavor is almost unimaginable, requiring technology and resources that are currently beyond our reach. But the hunt continues. Physicists are exploring innovative ways to search for gravitons, from looking for tiny ripples in spacetime called gravitational waves. These waves, first predicted by Einstein, have already been detected by observatories like LIGO, providing indirect evidence of gravitational interactions, to studying the behavior of ultra-cold atoms. By cooling atoms to near absolute zero, scientists hope to observe subtle quantum effects that could offer clues about the graviton. The quest to find this elusive particle is a testament to human curiosity and our relentless pursuit of knowledge. Section 7. A New Hope string theory and loop quantum gravity. While the direct detection of gravitons remains a distant goal, theoretical physicists are not sitting idle. New theories such as string theory and loop quantum gravity offer hope for quantizing gravity. String theory proposes that the fundamental building blocks of the universe are not point-like particles but tiny vibrating strings. Different vibrations of these strings give rise to different particles and forces, including gravity. String theory naturally incorporates gravitons into its framework. Loop quantum gravity, on the other hand, takes a different approach. It proposes that space-time itself is quantized, made up of tiny, indivisible loops. This theory also predicts the existence of gravitons as quanta of space-time. Section 8. Unifying the universe. The successful quantization of gravity would be a monumental achievement in physics. It would mean we finally have a single theory that can explain all known forces and particles in the universe, a theory of everything. Such a theory would have profound implications. It could help us understand the very beginning of the universe, the Big Bang, where both quantum mechanics and gravity played crucial roles. It could also shed light on the nature of black holes, those enigmatic objects where gravity reigns supreme. The quest to quantize gravity is a journey into the unknown, a pursuit of a deeper understanding of the universe and our place within it. Section 9. The future of gravity. The hunt for gravitons and the quest to quantize gravity are among the most challenging and exciting frontiers in modern physics. Scientists around the world are dedicating their lives to understanding this elusive force that governs the cosmos. While we haven't found the graviton yet, the hypothetical particle that mediates the force of gravity, and we don't have a complete theory of quantum gravity, the journey itself has been incredibly rewarding. Each step forward, each new discovery, brings us closer to a more profound understanding of the universe. The journey itself has been incredibly rewarding. We've learned so much about the universe, about the nature of space and time, and about the fundamental laws that govern reality. We've learned so much about the universe, about the nature of space and time, and about the fundamental laws that govern reality. The pursuit of a deeper understanding of gravity has pushed the boundaries of human knowledge, and will continue to do so for generations to come. About the nature of space and time, and about the fundamental laws that govern reality. The pursuit of a deeper understanding of gravity has pushed the boundaries of human knowledge, and will continue to do so for generations to come. The pursuit of a deeper understanding of gravity has pushed the boundaries of human knowledge, and will continue to do so for generations to come. The future of gravity research is bright. The future of gravity research is bright. with new telescopes peering deeper into the cosmos, with more powerful particle accelerators probing the smallest scales of matter, and with brilliant minds developing new theories, we are closer than ever to unraveling gravity's quantum mystery. The future of gravity research is bright. With new telescopes peering deeper into the cosmos, with more powerful particle accelerators probing the smallest scales of matter, and with brilliant minds developing new theories, we are closer than ever to unraveling gravity's quantum mystery. The future of gravity research is bright. With new telescopes peering deeper into the cosmos, with more powerful particle accelerators probing the smallest scales of matter, and with brilliant minds developing new theories, we are closer than ever to unraveling gravity's quantum mystery. The future of gravity research is bright. With new telescopes peering deeper into the cosmos, with more powerful particle accelerators probing the smallest scales of matter, and with brilliant minds developing new theories, we are closer than ever to unraveling gravity's quantum mystery. The future of gravity research is bright. With new telescopes peering deeper into the cosmos, with more powerful particle accelerators probing the smallest scales of matter, and with brilliant minds developing new theories, we are closer than ever to unraveling gravity's quantum mystery. The future of gravity research is bright. With new telescopes peering deeper into the cosmos, with more powerful particle accelerators probing the smallest scales of matter, and with brilliant minds developing new theories, we are closer than ever to unraveling gravity's quantum mystery. The future of gravity research is bright. With new telescopes peering deeper into the cosmos, with more powerful particle accelerators probing the smallest scales of matter, and with brilliant minds developing new theories, we are closer than ever to unraveling gravity's quantum mystery.